Thank you. Yes, Linda is here, but she only started with me 3 months ago. I did not think it was fair to put her in front of you just yet. Most of the results you'll see are due to the other PhD student, Anis Allahdiniyan, who is not here. And this was done as part of a program we call GAP, which is a Marie Curie program, which is being run from the Politecnico di Milano. So thanks to Laura Vergani and Federica Buccino. In fact, we have 2 PhD students on this particular part of the program, one based in Milan and one in Dublin. So moving on, let's see. Okay. So to measure stress intensity, everybody knows that you need a stress analysis, right? To find K, you normally find it either analytically with an equation, if the geometry is simple, or computationally with a finite element model or some kind of model, knowing the stresses in the cracked body. But of course, this is a very significant problem in practice, because in many cases, it's difficult to do an accurate stress analysis, because the structure is complex in geometry and loading, and sometimes you don't even know very well what are the applied loads that the structure is experiencing. So, for example, this concrete bridge, this complex metal component on the left, or the particular problem which we are looking at in this program, which is a trabecular bone. That's the spongy bone that you find on the inside of your bones. It's a very complex structure. Yes, you can make a finite element model of it, but it's a huge model with a lot of assumptions. By doing synchrotron imaging and loading the specimen in the synchrotron, we can find tiny cracks in this structure. Here's one, 100 microns or so in length, and we can watch these cracks growing. So we have great potential there for studying the toughness of the material. But, you know, the stress analysis is really difficult and suspect, okay? So wouldn't it be nice to be able to find K without knowing the stress? Well, you can. It can be found from the crack opening displacement. Now, this is a bit of theory, which is in all the textbooks. You probably, your lecturer probably mentioned it if you did a course in fracture mechanics, but it's not very much studied. It goes back to the famous Westergaard, who, amongst other things, came up with an equation that says that the opening of a crack, 2 delta T, depends just on the applied stress, Young's modulus, the crack length, and the distance x measured from the middle. So when x is 0, you're in the middle and you get the most opening. When x is a, you're at the crack tip. So if we simply substitute k is sigma root pi a into that equation, we've now got k as a function of the opening of the crack, Young's modulus, and these geometrical parameters. So suddenly we don't need to know the stress if we can measure that crack opening. Now, the current problem is that this only applies to one particular case, which is a central crack in an infinite plate in tension. Westergaard didn't derive it for anything else, and as far as I know, so far nobody else has come up with the equivalent of this equation for other types of loading, other types of bodies. So that's what we have been doing. Our aim is to investigate crack opening for different geometries and loadings, try to find some general solutions describing how cracks open under load, and we're seeing this very much in a practical sense, to develop a practical approach that would allow K to be found in a lot of situations, such as those ones that I already showed you, the concrete bridge and the metal component and lots of other things. So you can see how this could potentially be very useful in health monitoring and also in determination of fracture toughness in various situations. Just a point, because some of you might have thought of it, this is not the CTOD. Crack tip opening displacement is a well-known way of characterizing toughness in tough materials, usually metals, but we're not talking about that. We're talking about an elastic, essentially LEFM kind of conditions, and we're talking about the elastic opening of the entire crack face from mouth to tip, rather than just the opening around the tip. Oops, sorry. So, okay, so in problems like this, it's always nice to start by doing something where you already know the answer, okay? So the top 2 images are for something that Westergaard equation should work for. So we have a small ratio of crack length to width and various different crack lengths. So we're plotting that profile, a delta t as a function of x along the crack for different crack lengths. And you see they're very much the same shape. And if we simply normalize those, dividing by the crack length and dividing by the opening at 0, then they all fall exactly on the same line. And these are finite element results, so you see no difference. And they also are exactly predicted by the Westergaard equation. Okay, Westergaard was right, is what we've said so far. I haven't said much. So the next thing then is to look at narrower plates. So if we now vary A over W, so in this graph, we've got the same crack length, the half length of 1.5, and we're varying A over W over quite a wide range. So from a plate that's much wider than the crack length to one where 2A divided by W is just 0.6. So obviously those would generate very different K values, right? And yet you can see again the shape is similar, and if you normalize them again, they all fall on the same line. So that's the first new result, that the Westergaard equation still works exactly even for quite narrow plates with central cracks in narrow plates. We then went on to look at edge cracks, and something a bit more interesting happened there. So if you compare the crack opening profiles of center cracks and edge cracks of the same length, we've got a number of different edge cracks in there. We've got single edge notches, single edge crack, double edge crack, and so on. And you can see there's a bit of scatter, but they all fall on more or less the same line. And you see it's quite different. The edge, if you've got an edge crack, the edge opens a lot more. This is kind of intuitively what you might expect. And in fact, that part of the graph, that from 0 to 0.5 here, to halfway along the crack, is easily described by a straight line. Okay, whereas when you get out here, it's all Westergaard is pretty much working for both center and edge cracks. So we just found a simple equation to describe that straight line, and that's there. And then we went on and we tested quite a range of other loading, other types of specimens, including central cracks at an angle. So then you get shear loading as well as tensile loading, and so the cracked faces slide as well as opening. And we also looked at 3-point bending. And in all cases, we found that the results fell on one of those two lines, all the center cracks on this line, all the edge cracks on this. In order to do that, because we have different crack lengths here, what we did was we just used a simple normalizing function on the vertical axis. So we've got delta t multiplied by Young's modulus divided by k root a, just to bring those together. But it makes the point that they all have very much the same shape. So we're kind of happy about that. So here's a practical example. Here's an experiment that we did by taking a leaf from my garden, okay, and bringing it into the lab, cutting a couple of very sharp notches in there, and loading it, and hopefully that will start, the video will start to work now. No, it's gone on. Let's try that again. Let's go back. Here we go. And so you'll be able to see, these are about 3 millimeters long, those cracks. You can see the cracks opening quite clearly, and then of course a rapid brittle fracture. So why would you want to do that? Well, imagine you're a botanist wandering around in the jungle, and you find some leaf, and you want to know the toughness of the leaf. And they do this, actually. It's quite important. Toughness of leaves is quite important for ecological analysis. But you don't happen to have an Instron testing machine with you, so what are you going to do? So the specimen that you saw there was actually loaded just by me taking it in my hands and pulling it in front of the camera, right? Didn't need a testing machine. So with that very simple setup, you can quite easily measure the crack openings. And we plugging that into the equation, we got a fracture toughness value exactly the same as with conventional testing. So we've proved in principle that it can be done, at least for leaves anyway. What about other materials? Well, what you saw up to now has all been published as a paper, Allahdiniyan and Taylor in TAFMEC from earlier this year. So I'll just mention a couple of more recent bits of work that we're working on. Obviously, we want to try and extend this solution to more and more different cases, different crack geometries, different types of loading, etc. So here's an interesting one where you have a crack, but the crack is inside the body, but it's quite close to an interface, to a surface. So now, of course, the crack tip on the left will have a higher stress intensity than the crack tip on the right as that crack grows closer to the surface. And that will lead to a slight asymmetry in the crack profile, where it's sort of shifted a little bit over to the left, as A over B here, 0.8 being when the crack is closest to the surface. And we can predict that easily enough because it's just now two Westergaard equations, right? Or the same Westergaard equation with two different constants overlapping each other. So we can deal with that. Another one, and this is the work that Linda has now started on. Linda is at the moment just looking at notches. So she's done a series of finite element models with this kind of a notch with different radius to crack length or notch length. And what we're finding there is that you get more or less the same shape, as you can see. So the bottom one here, which has a very low rho over A value, that would be a crack, as you saw before. And then we've gone all the way now to a circular hole here at the top. And you can see we still get the same displacement of the faces of the notch. This is not including the actual machined shape of the notch. This is just how much it moves. And interestingly, the blunter notches show more displacement of the surfaces. But as you can imagine, we can find a function that describes that. And in fact, we think we have a first principle explanation of why that happens. But anyway, you can see it's going to be possible to extend the approach to look at the openings and movements of the surfaces of notches as well as cracks. How's the time going? Not too bad. So then we're just thinking about other materials and what kind of materials, what kind of situations would this approach be possible. What we're plotting here is the opening of the crack for cracks of different lengths, the opening of the crack just before it fails. Okay, so this is basically the maximum opening that you're going to see just before you reach the fracture toughness of the material and the crack propagates, right? And interestingly, a lot of materials are falling into the same band here. So in this group here, we've got polymers, we've got metals, we've got bone, we've got concrete, materials with very different toughness and different Young's modulus values. But this parameter of the opening at failure is actually more or less the same. And a few outliers. Rubber obviously opens a lot more, glass a lot less. And then that dashed line is our estimate of what would be the resolution of measuring equipment that you could use, which obviously varies depending on how big the crack is that you're looking at. If you're looking at cracks less than a millimeter, you're using some sophisticated method like this synchrotron imaging that we're using. If you're looking at very large cracks, like maybe a big, like that crack in the concrete bridge, then you use different equipment. But anyway, for most materials, you can see that the amount of opening is considerably more than the resolution of the measuring equipment that is available. So that's leading us to think that this method could be used in a very wide range of situations. So finally, we're calling this approach the crack opening profile, or COP method. And as I've said, by measuring the tensile opening and also any shear openings between the crack faces, it's possible to determine K with good accuracy, at least in the cases that we've already looked at, because there are lots of other cases to study. And so we're going to continue with this approach, making finite element models and doing experiments to try to generalize the approach so that in the future, in principle, any crack that you have anywhere, you can see it. If you can see how much is opening, you should be able to work out what the stress intensity on that crack is. So thank you for listening.